Good morning, students. The topic for today's class is data transfer and manipulation. As we already studied, computer provides instructions, and using those instructions, user can make computer system perform actions. The instruction set of different computers differ from each other in a way that operands are determined from the address and mode fields. Instruction set is not identical in every system. It is it perhaps depend on um, different factors, and the most differentiating factor is that how operands are determined from the address and the mode fields. The actual operations available are not very different. Every operation that you could perform on Intel machine can also be performed on Mac machines. Operations remain um, very much similar. However, the way in which operands are determined from the address and mode fields is different. So the basic set of operations available in a typical computer is the subject of discussion of today's class. Most computer instructions are classified into three categories: data transfer instructions, data manipulation instructions, program control instructions.
Ma'am, maybe someone wants to join the class. Will you check that once?
Yes, yes. All right. They have joined. We are trying to understand here computer instructions. These are classified into three categories: data transfer instructions, data manipulation instruction, and program control instructions. Data transfer instructions transfer the data from one location to another. The question now to students is, will you tell me so far what uh, instruction we have learned that could transfer the data from one location to another?
Ma'am, we learnt about that register transfers now.
Yes, instruction you tell me. Instruction means or operation. Yes, students, please try.
Ma'am, sorry, ma'am, couldn't get the question well.
Uh, we have learned uh, opcodes, operations that will fit in the second part of the instruction register. In that, from that set, which are data transfer instructions or operations. Opcode we learned to know memory reference instructions. In memory reference instructions, we have seven kinds.
Yes, ma'am, we learned that.
Tell me any one instruction that would perform this data transfer operation.
Can we use move?
Yes, move.
TSFA, ma'am.
Yeah, very good. Move. MOV is a data transfer instruction. And any other?
Ma'am, the TSFA transfer A.
Transfer A. Transfer A, that is the description, no? Is there any such instruction? Anyone is willing to try? Like MOV, we also have some other instructions that can transfer data from memory to accumulator, accumulator to memory. Well, uh, let us discuss. Load, LOAD, load is the name. Here, the mnemonic uses LD. Which mnemonic was used in the previous chapter for loading? Well, it is LDA. For store, STA. Push, pop, we used push and pop. Input and output, INOUT. Uh, all we learned. Load, store, move, except exchange. Input, output, push, pop. Exchange is occurring here, uh, for the first time. XCH. Otherwise, with LDA, STA, MOV, INOUT, push, PUSH, POP, these are data transfer instructions. Data transfer instructions are those instructions that shift the data or move the data or transfer the data from one location to another location or one place to another place. Move the data. Data transfer instructions move data from one place to another without changing the data content. Data is not changed. Data remains as it is. You are just moving it from one place to another place. Load instruction has been used mostly to designate transfer from memory to a processor register. Memory to a processor register means from RAM to accumulator. Store instruction designates a transfer from processor register to memory. Typically, it's accumulator to RAM. Move instruction has been used in computer with multiple CPU registers to designate transfer from one register to another register. Exchange instruction swaps information between two registers or a register and a memory word. If in memory, if it is 2 and in register it's 4, if you call XCH exchange, 4 would go into memory, 2 would come to register. Input and output instructions transfer data among processor registers and input or output terminals from keyboard to accumulator or accumulator to monitor is input and output. Push and pop instructions transfer data between processor registers and a memory stack. There are processor registers like R1, R2, R3, or even accumulator. or any other register between processor register and memory stack. When there is a transfer of data, push and pop instructions are used. Uh, Students, we have learned addressing modes. Do you remember what addressing modes have been covered earlier? Will you quickly list out the addressing modes?
Direct, indirect,
Direct, indirect,
implicit, ma'am.
implicit.
Derived.
Is there any addressing mode derived?
Zero also. Zero register addressing.
Immediate register mode.
Yeah, immediate register. Yes. Next. Yeah, students, please try.
Direct,
Direct.
indirect, indexed,
Yeah, indexed.
and increment and the decrement.
Register. Auto increment, auto decrement. Those are register mode operations.
Immediate inclinal.
Immediate, implied,
Register.
register mode.
Relative, ma'am.
Yes, relative.
Auto increment, auto decrement mode.
Yes, yes. Very good. These are the addressing modes. The mnemonics for load immediate would become LDI. Load immediate is for immediate addressing mode. Immediate mode is recognized from a pound sign placed before the operand. Load to accumulator instruction used with 8 different addressing modes. The syntax is given in this table. Load means getting a value from memory or any other method using any other addressing mode into accumulator. To do that, these are the assembly conventions. Assembly conventions means when you write a assembly language program and you need to specify which load you are trying to use, in the sense that which addressing mode you are using in order to load the data. There are different conventions used. Here, the meaning is also given. Direct address, LD. LD is the instruction. LD. ADR. ADR is the address in memory, which evaluates to AC equal to accumulator is equal to M of ADR. M means memory. Memory of means this address. ADR denotes the address of the memory. That um, value stored in memory pointed to by ADR is brought into accumulator. Indirect address is denoted by at the rate symbol LD at the rate ADR. And what does this evaluate to? It's evaluate to M of ADR would give a value which is the address, which is the effective address of the operand. Therefore, that is taken again as parameter for memory, which is M. So it is M of ADR, which is indirect address. Relative address is LD, this dollar ADR. Relative address implies that the contents of PC is added up to the contents of uh, uh, address part of instruction, which is ADR. ADR is the address component of the instruction register um, that is added up to the program counter. Together uh, uh, would identify the address of the memory, which yields to the operand stored at this memory location uh, that is brought into accumulator. Relative address is denoted by dollar. Immediate operand. Immediate operand is this hash upon sign, this hash sign, load hash NBR. What is NBR? NBR is the actual operand. Where do you find this actual operand? In the instruction register itself. In IR, the address part, instead of containing the address, would have the operand, say 10, that is loaded. Index addressing is denoted by ADR within parenthesis X, which evaluates to ADR, which is the address part of the instruction register, plus XR. XR is that our register. There is a register, um, index register that would hold a value that is added up to the address part of the instruction register, means ADR address plus XR, value of XR, together identify the memory location from where the value has to be brought into accumulator. Register implies that the value or the operand resides in register. Here it is R1, AC equal to R1. Register indirect, which means that register holds the address in the memory which holds the operand. So M of R1. This M is memory. Memory of R1 is the address part which we can find in R1. That is stored in the operand or the value stored at M of R1 is uh, brought into accumulator or transferred to accumulator or moved from that memory into accumulator. Auto increment is denoted by LD within parenthesis R1 and there is a plus symbol which implies that after the value is accessed, which value, the address value stored at R1 is accessed, it has to be incremented. It comprises of two statements. First one is M of R1. M of R1 is the memory identified by address R1 that will hold an operand that is transferred to AC accumulator simultaneously. R1 value is incremented, R1 equal to R1 plus 1. Do you understand these 8 addressing modes for the load instruction?
Yes, ma'am.
Students, if you have any doubt, you can ask. That was about data transfer instructions. There are three categories of instructions: data transfer instructions, data manipulation instruction, program control instruction. In data transfer instructions, we looked at 8 different kinds of data transfer instructions, and their meaning also was discussed. Further, moving on to data manipulation instructions, which is the second kind of computer instructions. Data manipulation instructions perform operations on data and provide the computational capabilities for the computer. The data manipulation instructions in a typical computer are divided into three basic types: arithmetic instructions, logical and bit manipulation instructions, instructions. Data manipulation instructions are all about performing some kind of computations on the data, which include arithmetic operations, logical and bit manipulation operations, and shift operations. Arithmetic instructions. The four basic arithmetic operations are addition, subtraction, multiplication, and division. And most of the computer provide instruction for all these four operations. The table listing out arithmetic instructions are: increment operation denoted by INC. This is the mnemonic. Mnemonic is the symbol assigned to the operation that can be used in assembly language programs. Decrement, DEC, add, ADD, subtract, SUB, multiply, MUL, divide, DIV, add with carry, ADDC, subtract with borrow, SUBB, negate, that is two's complement, NEG. These are typical arithmetic instructions in a computer. These three are the mnemonics for three add instructions that specify addition operation on different data types. Add I, just add is for addition, that is general addition. However, to restrict it to a particular type of number, there are three variants. Add I is to add two binary integer numbers, add F is to add two floating point numbers, add D is to add two decimal numbers in PCD. These are arithmetic instructions. Logical and bit manipulation instructions are given in this table, which are clear, CLR, complement, COM, and AND, or OR, exclusive OR, XOR, clear carry, CLRC, set carry, SETC, complement carry, COMC, enable interrupt, EI, disable interrupt, DI. All we learned with different mnemonics in earlier chapters. If you have any doubt, you can ask. What are shift instructions? Students, this is a question for you. What are shift instructions?
Shift left and shift right. Circular
Yes,
left shift and circular right shift.
yes. One more. Arithmetic.
Arithmetic shift left.
Arithmetic shift, ma'am.
Right. Very good. You can um, look at this table. These are typical shift instructions. Logical shift right, SHR. Logical shift left, SHL. Arithmetic shift right, SHRA. The mnemonic that was given was different in earlier chapter. Here it is different, but then the essence is same. It performs arithmetic shift right, arithmetic shift left, SHLA. Rotate right, ROR. Rotate left, ROL. Rotate right through carry, rotate left through carry, RORC or ROLC respectively. These are instead of circular shift, here the name given was rotate right, rotate left, and rotate right through carry, rotate left through carry. All right, that was data manipulation instructions. Program control. Will you name few program control instructions which we already covered? Students, this is a question for you.
Branch,
Very good. Branch.
skip, call,
Very good. Those are
compare.
program control are branch unconditionally, branch and save return address, ISZ, compare. So these are the program control instructions. Branch, BR. Branch we studied there are two types, branch unconditionally, BUN, BSC.
Additionally,
Here the journal branch is given BR, jump JMP, skip SKP, call CALL, return RET, compare CMP, test EST. Uh, these are program control instructions. And what are status bit conditions? What is the need of status bit conditions? Status
ma'am, in
bits.
previous
Mm,
examples, they are used to show whether the number is positive or negative by
very
using that
good.
extra carry.
Very good. Very good. These are also known as condition code bits or flag bits. Here you can see bit C carry is set to 1 if and carry C8 is 1. It is clear to 0 if carry is 0. That is carry bit. Sign bit. Sign bit is 1 for negative, 0 for positive. 0 if all the bits in a register is 0, it would be set to 0. Otherwise 1. Overflow if in case the result is not being mm, you know stored completely in a register and there is a overflow bit, then overflow will be set to 1, otherwise 0. These are status register bits. A and B are two numbers, each 8 bits long. This 8 bit ALU, arithmetic and logic unit, and these bits CSZV, carry, sign, 0, overflow. These would be set based on whether there is a uh, eighth bit coming out, means it would be carry. If 7 bit is set one is 1 means sign bit is set. If Check for zero output. If all bits are zero, then zero would be set, z would be set to zero. And overflow, if you perform XOR operation between C7 and C8, and if it gives a value 1, then there is overflow that is set here. This is status register bits. Conditional branch instructions. Uh, Conditional branch instructions would would make the would make the system to branch to another location based on certain conditions. What are the conditions that are tested here? Tested condition is z equal to 1. Z equal to 1 means branch is 0. Mnemonic is bz. Z equal to 0 means branch if not 0. B and z. Branch if carry. Branch if no carry. Branch if plus. Branch if minus means positive number, negative number. Branch if overflow. Branch if no overflow. Those status bits or condition bits are tested to perform the action uh, based on the result that is obtained from the testing operation. Unsigned compare numbers A minus B. Unsigned numbers you are comparing. Unsigned numbers are those numbers which are all positive. Signed numbers are those numbers which are a mix of positive and negative. If A greater than B, it means A is higher. A greater or equal to B, A is higher or equal to B. A less than B, A is lower or less than B. And you observe here, these are the operations BHI, BHE, BLO, BLOE, B, BNE. B is if both are equal, BNE is both are not equal. Signed compare condition A minus B. This is for signed numbers. A greater than B, A greater or equal to B, A less than B, A less than or equal to B. Here BGT, BGE, these are for signed numbers. These are for unsigned numbers. These are testing conditions, and based on the outcome, action is performed in the form of this instruction. There is one numerical example given here. Consider an 8-bit ALU shown in figure. The largest unsigned number that can be accommodated in 8 bits is 255. Will you tell me, students, what is the meaning of this? The largest unsigned number that can be accommodated in 8 bits is 255. How we got this 255 value? Anyone of you? Yes, students. You know
What,
it.
ma'am?
In a 8 bits register, what is the largest unsigned number that we can have in a 8 bits register? Unsigned number means it is a positive number. 1, 2, 3, 4, 5, 6, 7. 127. Why are you saying 127, Sirisha? What is the basis?
Sorry, ma'am, it's range, I think.
Hmm? It is?
Range.
There is 8 bits register. Alright, 8 bits register. How many slots 8 bit register would have?
8 slots, ma'am.
8 slots. How you can fill those slots? Yeah, yeah, what is the range? Okay, let us take range. What will be the range? Students, you know it. Think and let me know. Okay, if it is 2 bits register, what is the range?
2 raised to power 2.
2 raised power 2. 2 raised power 2 is what value?
4.
4.
4. 4 means what is the range? How do you begin uh, a number in this configuration?
0,
0.
0 to
Uh,
3, ma'am.
0 to 3. Okay, you got the correct answer. Now tell me for 4 bits.
0 to 31. Sorry,
0
sorry.
to
0 to 15.
0 to
0
15,
to.
ma'am.
Now say about 8 bits.
0 to
0 to
255.
Very good. 0 to 255. So that is what is given here, 255. Because the total number of bits you can have is 256. Because you begin with 0, so 0 to 255. The next question that arises is, this is uh, for those registers in which all the bits are used to store the number. But consider that if you are not using all the bits to store the number, rather you are using one bit to store the sign. What would be the range? The register size is 8 bits only, but then you use one slot for uh, for the purpose of storing the sign bit. Sign. What is the sign bit? Sign bit will denote whether the number is positive or a negative. If you store 0, it denote that the number is plus. If you store 1, it denotes the number is minus. Can you tell me the total numbers stored and what is the range?
0 to 127, ma'am.
Hmm. Very good. It is not the 0. It
Okay,
is
ma'am.
not.
We are considering negative number also, na?
Yes. So
Okay.
minus 128 to plus 127. This is the range. And because we have the range of signed numbers is plus 127. Plus 127 and minus 128. Or you can say minus 128 to plus 127. This is the range of a signed number. This is known as signed number. And 0 to 255 is known as unsigned numbers. Is this point clear to you all students?
Yes, ma'am.
Yes, ma'am.
Hmm. Very good. Look at here. A. What is the number of A? Tell me the number in decimal. What is that? Uh, what is this binary number converted into decimal form? And what is this one?
Ma'am, shall
We are,
we have to consider that first one in binary number also?
this is signed two's complement representation.
Signed to two's
Thus,
complement. Huh?
signed two's complement. Uh,
So it is a
this is
negative number.
A, this is B, and to perform A minus B, um, what are the steps to perform A minus B? Do you remember the steps to perform
Yes, ma'am.
subtraction?
First two's complement, then adding.
Two's complement of minuend or subtrahend? Which is minuend and which is subtrahend? If you say A minus B, which is minuend and which is subtrahend?
Ma'am, A is manuand and B is subtrahend.
A is minuend and B is subtrahend. Very good. Now what is the first step?
Taking two's complement of subtrahend
Yes, take two's complement of subtrahend
and add it to A.
and add to minuend. Okay, next. Second.
That's it, na ma'am, for subtraction.
No, second. There are
Add
three
1 to
steps.
the result.
Why do you add one to the result? Okay, after this you get the result. That's right. But you have to verify, whether the result is positive or negative. How do you verify whether the result is positive or negative?
Mm, by that extra carry, ma'am.
By that extra carry. So if A is greater than B, an extra carry is generated. There is a carry. When there is a carry, you discard the carry and take the result. Otherwise, if A is less than B, what happens in this case?
No carry, ma'am.
There is no carry. If there is no carry, then what happens?
Considering the entire.
Considering the no, if there is no
Result,
carry,
ma'am.
what is the result? What is the result if there is no carry? You have to think and tell me.
That means the result is no carries. Positive.
Result is
Positive, ma'am.
positive or result is negative.
Negative.
Result is negative. If A is less than B, it means that result is negative. If result is negative, you have to take 2's complement to find the actual result. There are three steps. First step is takes 2's complement of subtrahend and add to minuend. In case A value, this upper value is greater than this lower value, there is a carry generated. Discard the carry and take the result. When A is less than B, the result is in negative form, which is in 2's complement form. Further, obtain the 2's complement of result to obtain the value value of subtraction. All right. So then, can anyone tell me now here what is happening? What is A? A is
What, ma'am?
this: one, two, three, four. Four ones and four zeros is A. Four ones and four zeros. What is the decimal value? 1, 2, 4, 8, 16 plus 32 plus 64 plus 128. How much it will be? 16 plus 32, 48. 48 plus 32,
240.
64. 240. Okay, right. So it is 240. And what is B here? One, 2, 4, 8, 16. 16 plus 4, 20. You have to perform subtraction. To perform subtraction, you are obtaining the 2's complement of 20, which is equal to uh, 3 zeros, 1 0 1 double 0. 1's complement is 1 1 1 0 1 0 1 1. Add 1 to this, you get 0, carry 1 0, carry 1 1 0 1 1 1. So 3, no, wrong. 1 plus 1 0, carry on. 1 plus 1 0, carry on. So this is 1, this is 1, this is 0. 3 ones, 0, double 1, double 0. Yes. So this is 2's complement of B. When you perform addition, 0 0 0 0 0 0 0 1 1 0 1 1 1 0 1 1 1 0 carry 1. 3 ones means 1 carry 1. Uh, 1 and there is 1 carry. Okay. There is 1 carry. So what you got? So carry is 1. Carry given here is 1. What is the result? Result is 4, 8, 16, 32, 64, 128. 128. This is 220, right?
Yes, ma'am.
So we are studying actually the condition bits. To understand the condition bits, we have taken this example. What are condition bits? 4. What are they? Carry, sign, overflow, 0. Here there is a carry. Because there is a carry, C equal to 1. And because this final last bit, um, this is known as high order bit. If because this bit is 1, sign is 1. And there is no overflow because you could accommodate the result within these 8 bits. Overflow is 0, and because all if all is 0 means here it will be 1. It is non-zero, so Z is 0. Did you understand this example with the use of condition bits?
Yes,
How
ma'am.
we can use condition bits with the example?
Yes, ma'am.
Subroutine call and return. I think this is a big topic. We will study this tomorrow. This we will study tomorrow. This topic of subroutine call and return, followed by program interrupt and so on. Any doubts, students?
No, ma'am.
Have you completed the notes?
We are writing it, ma'am. Actually, till yesterday we were writing our assignment.